so our point charge. And I have a charge here. And a charge here. And a charge here. And a charge here. All the same. We're not going to do this problem. I want you to see something as we transition. If we assume that they're spaced in some uniform way, will you agree that this problem has many similar characteristics to the last problem? That we're likely to have a force that is 0 at the center, but also diminishes if we get further away. The difference, of course, is that I have 4 forces acting on my point charge, but I have exploitable symmetry that I can use here. Now, without doing any work and just using that symmetry to my advantage, can you buy into the fact that that's got to be the force from the 2 inner charges? And this would have to be the force from the 2 outer charges, because the only thing that's changed is the triangle information a bit. Do you also realize then that if I had 100 charges, 50 on the top and 50 on the bottom, I would just be adding more terms here, with this number changing as I add more and more and more particles getting further and further away from the origin, right? I can exploit the symmetry, and I can exploit the geometry that I already know about. Does that all make sense so far? Well, what if instead of having point charges here, what I actually have is a bar where the whole bar has a charge Q spread out uniformly on the bar. These problems are known as charge distribution problems. Charge distribution problems. And they are more realistic than point charge problems, because most of the time when we deal with collections of charge, they are distributed on an object. And therefore the object itself is a distribution of charge. You're going to hear me say this phrase all the time. Let's make the assumption that the whole bar is length 2D with half of it on the top and half of it on the bottom. Now, you noticed in the last example that when we went from 2 charges to 4 charges, we just simply added the 2 charges that were the inside and the 2 charges that were the outside. And you agreed with me that if we had more, we would just continue to add the pairs of charges together. Does that make sense? We're going to do the same thing here, but it's going to require us to be a little bit more creative in our mathematics. Whenever we have a problem that involves a distribution of charge, we're going to have to take our problem and break it up into small pieces that we define for the purpose of creating something that we can add together. Meaning we're going to have to create variables that won't be in our answer, but that will be used for the purpose of making our sum. You follow what I'm saying? This might not be something that you guys can do right off, and it might take a little bit of time. But if you don't know where this is going, again, I remind you what we just had just a moment ago. Our answer looked like this. Putting it up here for a reason, because if you are really paying attention and you're a mathlete here, you understand that we could just keep extending this, right? Do you also realize that for the most part, this part never changes? And what we have inside this parentheses is just something that continually expands as we add more charges. All right, so it's a summation, and a summation that has some term in it that is increasing. It's going to be 4. The next one is going to be 9. You know, I can probably you could probably recognize it's going to be all the squares of the integers in there. Right? Does that sound familiar to you guys? Because it's adding some kind of incremental increase. Do you guys remember doing stuff like this in pre-calc? These kinds of incremental formulas? That's supposed to be training for how to handle this. Okay? Now, I'm going to give you kind of a reasonable set of steps on how to deal with a charge distribution problem. We are not going to see the math all the way through. We're going to see the math up to a point and stop. All right? And you'll understand why, especially if you've already had a course in calculus. You'll understand why we're going to stop. What I need you to do is understand that calculus is the toolkit that allows you to execute what we are going to create. But what we are going to create is not taught in calculus. This is the physics portion. This is how we approach a problem like this and break it up in such a way that we can create a mathematical function that will solve it. Sometimes the functions we create are unsolvable, meaning there is no calculus that will easily do the integration or the differentiation that must be done. That doesn't matter. Your job is to get it to a point where it can be integrated or it can be differentiated. Does that make sense? All right. The first thing I want you to understand is Coulomb's law only can handle a pair of charges at a time, not a distribution of charge. So the first thing you have to do is decide point. So I've quite literally just drawn a square, and I'm going to say that this is a piece of the entire bar. And I don't mean that in haphazardly. I'm going to use a symbol that represents a piece of the total charge. Now, the symbol that we would normally use in algebra would be a delta, because a delta is a piece, but we're going to use the calculus version of that, which is just a lowercase d times the variable that we're taking a piece of. So dq represents a piece of the overall charge. If I add up all of the dq's, I will get the total charge, which is q. Everybody understand? Any question about that? So, step 1, and I'm not writing these steps out, you should. Step 1 is to take your distribution of charge and find a piece of it that you will use as a placeholder for your problem. Now, in all of our work, when it comes to distribution of charges, we are attempting to create a formula that is geometric. The reason is because we can define the location of every piece a lot easier than we can define the amount of charge at every piece. And it's much easier to integrate something that has a shape. Integrating across a shape is easy because we can define the parameters of the shape. For example, this shape is linear, right? It's a one-dimensional object. And I know its size, it's 2D. And I know that it extends with 1D above the x-axis and 1D below the x-axis. I know a lot about its shape. So it's easy for me to figure out the limits of where my sum is going to be. Because we're going to be adding, just like we did a moment ago. In fact, I can say to the whole class that, well, I'm going to start with a piece over here, and I'm going to add up every piece until I get over here. And all those pieces together are going to be what I'm going to use to figure out the total force on my charge. Everybody understand what I'm trying to say? All right, so I have defined a piece. Now, the next part is I need to create variables that I can use in the execution of this sum. These variables will not be allowed in our final answer. Our final answer is only going to be able to have things like D, Q, Q, and probably X. Right? These are the things that can be in our answer. But the variable I'm going to create right now is a temporary variable that's going to be allowing us to do this sum. I'm going to use a distance because I think that's a good idea here. I want to define where this particular piece is. I'm saying that because we know from our other experience that how far away this piece is from the axis makes a difference in the answer. And I'm just going to define it as y. Right. So, step 1, have a piece. Step 2, try and figure out where this particle is and create a variable to tell your problem where it is. The next part's a little harder to understand at least. I would like to define the size of this piece with the variable I just used. I know it has dq worth of charge, but what I need is something that tells me how much charge there is based on y. So I'm going to say that this piece is a little more in the y direction long. dy is a length, and I'm using a variable that I created as a means of defining the size of this piece. Now, why I want to do that might not be clear, but I think it'll be made clear when you see the next 2 steps. Now, in your notes though, since these notes are going to be reused, I hope, if the object is one-dimensional, you're going to be making a length, dy. If the object is 2-dimensional, you'll be making an area, dA. And if your object is 3-dimensional, you'll be making a volume, dV. And you may have to find ways of defining the area and the volume. We're kind of fortunate in that this is just a one-dimensional object, so all we have to do is define a length. But our next step is to define how much charge there is in terms of how big the piece is. Okay, our next step, I'm watching Mary struggle over here. I just got to put it aside. This next part, a lot of students struggle with it, but it's not that big a deal. We have to find a way of figuring out how much charge there is, but we want that amount of charge to be based on things we know about our charge distribution. So this one, we're just going to make a ratio. It's the easiest way to show this. I know that the amount of charge I have is related to how big the piece is. That's a ratio, right? Charge to length. This has to be equal to the total amount of charge I have divided by the total length of the piece. We are creating what's known as a charge density. How much charge is there per unit length? This is a charge density. If we are assuming that our object has a uniform charge density, those 3 words, super important. If we're assuming that our object has a uniform charge density, you want to hear that as part of the problem, a uniform charge density. That means any piece of the object should have the same charge density as any other piece of the object. So if you remember way back from chemistry, density is just amount divided by volume. We have 3 different kinds of densities. We have linear density, amount divided by length. We have surface density, amount divided by area. And we have volumetric density, amount divided by volume. 3 different kinds of densities. As an aside, anybody who had mechanics knows this, but you guys who didn't have mechanics don't. We have symbology that goes with all of that. You didn't learn the symbology in chemistry when you did volumetric density, but there is a symbology here. We use lambda for linear density. We use sigma for surface density. And we use rho for volume density. In mechanics, we use this only when we were talking about moments of inertia and center of mass. And we didn't use it very much. I need to make sure you understand we will use this all the time. Most of the problems we have in here will have just a linear density or a surface density, but if the surface density is uniform, you probably won't need to use these symbols. They will probably give you things that you can use to figure out what they are. But they don't have to give us one that has a uniform charge density. They have given us problems before where the charge density, say, increases from one side of the object to the other side of the object. That means our charge density is a function of where you are on the object. So we'll start super clear and basic. Everything we're going to do for a long time is going to have uniform charge density. But you need to hear that said in the problem. You need to hear the phrase uniform charge density so that this is a constant anywhere on the object. Okay, we've done some of the heavy lifting here, so here's what comes next. We want to solve this for dq. So not much to do here, but we're going to solve it for dq. So dq equals q over 2d dy. Now, what we've done is we have found a way to isolate a single piece of our object, and we have found symbols that we can use to define how much charge is there. Next, we employ Coulomb's law. This is the first time we're going to actually do physics. We're going to employ Coulomb's law. There is a force from this piece of the bar on my point charge. And that force, assuming everything is positive, that force will be in this direction. I can write an expression for what this force must be. However, this is just one piece of a lot of forces that are acting on the object, right? There's another piece of the bar over here that's doing the exact same thing, right? It's causing a force on the bar, on that point charge. So what I want to do is write how much this force is, and I'm going to write it with a little d in front of it, saying that this is just a small part of the total force. dF. I'm recognizing it's just a piece of the force. I'm going to write Coulomb's law with that in place. A piece of the overall force is going to be equal to the point charge. We know that that's one of the charges that we have. The piece of charge, k, over the separation distance squared. Now, I want to add this up for every piece of charge. Like that's what the point is here. I want to add them all up. This is just one of those pieces of charge. Now, here's the point. I have two variables. For every q, there's a different r. Would you guys agree with that? I am noticing that there's a certain amount of symmetry here. And because there's symmetry, I may not be as interested in df as I think I am. Meaning, I'm probably more interested in just the part of the force that's in the x direction. Because aren't the y parts going to cancel out? So maybe I don't have to sum for df. Maybe I need to sum for df in the x direction. Because I'm pretty sure that when I sum for df in the y direction, I'll get 0. Right? There's no force in the y direction because there's equal amounts of bar on both sides. So I'm going to do the same kind of thought process as we had a moment ago. I'm going to say there's a component of the force along the x direction, and there's a component of the force along the y direction. I don't know why that happened. And I am only interested in the one in the x direction. I'm not interested in the one in the y direction. So I'm going to put down here that my force in the x direction is probably the force in the y direction times the cosine of theta. All still good? Everybody follow along with that okay? All right. Now, I have a function. I have an addendum to that function, and I have a way of expressing the charge in terms of position. You need to bring all of these things together and try and convert this into one relationship where only one variable is changing. Because right now, when dq changes, both r and theta all change, right? 3 different variables are all linked together, and they're all changing whenever I choose a different charge. I need to find a way of writing this in terms of only one variable that's changing. For example, I already have an expression that would allow me to convert dq into something that has y in it. I think my next job would be to find a way of expressing cosine theta in terms of something that has y in it. Because if I do, then I can replace cosine with something that's in terms of y, and I can replace dq with something that's in terms of y, and I am also very sure I can express r in terms of y. Right? Get all of these variables in terms of one variable that changes. So for example, let's deal with r, because r is the easiest, right? Isn't r just going to be y squared plus x squared to the 1/2 power? Right? Just like we did yesterday. You guys see that okay? You guys all okay with that? All right. Can you do the same thing for cosine theta? Can you express it in terms of y? You should be able to if you've been paying attention. Everybody see that okay? So I've now expressed cosine theta in terms of y. X is the variable I'm allowed to have. And I've expressed r in terms of y, and I have dq in terms of y. I'm going to rewrite this force equation in terms of y. So slide that over there. All right, it's going to be messy, but q times q over 2d dy times k divided by r squared times cosine theta All right, does everybody see what I've done? All right, so I've got df in terms of a collection of constants and one variable that I have to sum over, y. All right, y is the variable that defines where each piece is. And I need to add it up for all the pieces. Now this is a mess. I mean, a total mess. However, a lot of these things don't depend on y. So what you should do next is take out everything that doesn't depend on y and separate it from the rest of the expression. So let's go through. Does q depend on y? The point charge? No. Does capital Q depend on y? No. Does dy depend on y? Yeah. Does k depend on y? Does x depend on y? No. Does 2d depend on y? Unfortunately, y squared plus x squared depends on y. And I can't separate out the x squared from that because it's a sum. So I will have 1 over y squared plus x squared to the 3/2 power. And I'll put the dy at the end for convention. I'll always put the dy at the end of one of these things. Whatever your d variable is goes at the end of one of these things for convention. Now, you guys who have had calculus know that we are creating an integrand here. You guys who have not had calculus, we are creating an integrand here. It is a challenging thing to do in this class, something we will struggle with the entire year. And I know I'm starting at day 4 of instruction, but it is that important that we nail this. All right? None of this is taught in calculus. What calculus is do is the next part. Because the next thing for us to remind ourselves about is that we now need to add this up for every piece of the bar. So I'm going to do exactly that. I'm going to put a summation symbol on both sides, saying I'm going to add this up for every piece of the bar. You'll notice I put the summation sign on the right side because I'm in between there, because none of those constants change. I put it in front of the thing that I know is dependent on y. On the left side, if I add up every single piece of charge, this will be just the total force in the x direction. That's the left side. That symbology is to tell me I need to add it up for every piece. The right side, well, this is all great, fun and good, but I need to now tell the integrand where the first piece is and where the last piece is. So there's a couple ways we can do this. You guys who have been around this a little bit know that there's a couple of things you can do. We can say that the first piece is located at negative d, and the last piece is located at d. That's one way to do this, and that will be successful. If you've done this a while, though, you probably also know some other tricks. Like, it's almost always easier to integrate if you can put a 0 in there someplace. So since our bar is symmetrical, I think we get the same contribution to the force from the top portion of the bar as we do from the bottom portion of the bar. Would you all agree with that? So we could also consider just saying, all right, I'm just going to do half the bar and multiply my answer by 2. These are not tricks. It's a sum. And because it's a sum, you can do half the sum and double it to get your answer if there's the proper symmetry, and we have the proper symmetry here. Now, this is where we stop. You guys who have had calculus, try this, please. This is a bear. You'll know why it's a bear the moment you start. You can't use you can't use U sub here. So if you're hoping there's a nice U sub for this, there is not. For U sub to work, I would need to have y in the numerator somewhere, and I don't. So this is not easily integratable. It requires an interesting set of trig identities to actually integrate this. But I have super smart people who claim on a regular basis to be mathletes and know way more than me. So for all of you who like to shove it in my face about how smart you are, I expect to see an answer by tomorrow. You'll do it out of spite. I'll do it by looking it up on a integral chart, because I don't want to do all the substitution. I know what the answer actually looks like, and it's a bear. It would be easier if this was an infinite bar, believe it or not. But because it's not, and it's a finite bar, oof, this thing's rough. This is a rough answer. So you guys who have had calculus, this one's tough. And you guys who have not had calculus, you will never be expected to do an integral in this class that isn't either a simple integral or allows for a simple U substitution. All of ours are going to be basic integrals. And you're provided with an integral table. So anything that is going to be integrated in this class, the integral table will tell you how to do the integration.